students, we are going to discuss about optical properties in the lecture 27, and probably this will be the last lecture on properties of nanomaterials. If anything is required to add it, I will do it bits and pieces, otherwise we will move into next things of the course. So, lecture number 27, we are going to discuss about the optical properties of semiconductors and metallic materials. You know, this discussion we have started in the last lecture, and in the last lecture we talked about optical spectra of semiconductors. I brought in a new concept called exciton, which you may not have heard earlier, and then tried to explain the optical spectra of the semiconductors using three important aspects. First, what is the important aspect we consider? First important aspect is the density of states, right. Density of states is the first important thing which require to discuss about the interaction of the light with the electrons. But you know, density of states, the valence and the conduction bands also affected by the size. So, that means the quantized energy levels of the nanostructure, nanoparticles or nanostructures are going to be playing the predominant role in deciding the optical properties of the material. And third important thing is obviously exciton. So, remember these three are the critical factors controlling the optical properties of different nanomaterials, right. But you know, out of these things, density of states, where the electronic state levels in the valence and the conduction band plays the predominant role. At the same time, exciton has an important role in the spectra, optical absorption spectra coming at a higher wavelength. Fine. So, that is what something which we did in the last lecture. So, as you know, electromagnetic spectrum is pretty large, starting from gamma rays on the one side and then radio waves on the other side. Gamma rays are very small wavelength of the order 10 to the power minus 14 to 10 to the minus 12 meters. On the other hand, radio waves are like meter long, okay, or a couple of hundreds of meters possible also. Light actually comes with a very small energy electromagnetic spectrum, that is between 400 to 700 nanometers. And by optical properties, we are talking about this range of electromagnetic spectrum, right. So, therefore, you know, the blue or the violet is on the lower wavelength side, that is between 400 to 500 nanometers, red on the higher wavelength side, that is about 700 nanometers. That is something which you should remember always in your life, right. Now, how does the radiation, any radiation actually interact with material? The intensity of any electromagnetic radiation is I, is obviously proportional to the square of the amplitude of the radiation, and it has intensity I0. Then when it falls on a material, a part of it is reflected, part of it is absorbed, and part of it is transmitted. Okay. So, therefore, if I have to do a conservation of this energy, then it will be IR plus IA plus RT is equal to I0. So, now question is absorption. That is very important aspect in optical spectra. Radiation can penetrate any material, then it is absorbed, right. So, greater the thickness x through which the radiation can pass through, greater is the absorption. And common understanding or the experimental understanding indicates that absorption varies like this: I is equal to I0 exponential minus beta x, where beta is the absorption coefficient. Absorption coefficient obviously will depend on the wavelengths, also it will depend on the type of material and thickness, right. So, obviously, these are the factors which controls. Now, what is the next thing? Next thing is transmission. Transmission means what? The radiation must pass through a material. So, that means when it passes through materials, it will be lost some intensity of reflection on the surface when it enters, and then rest is transmitted and absorbed. So, absorption is written like this, okay. I is equal to I 0 and then within bracket 1 minus I r by I 0 square into exponential minus beta x, and this term which is occurring twice, I minus 1 minus I r by I 0 is because it is intensity lost, a reflection from both the surfaces, okay, that is why. So, that must be taken out. So, R transform stands for reflection, okay. So, therefore, transmission is intensity can be obtained simply by this equation. Now, what is the third thing? So, before we go for that, let us talk about, let us little bit discuss about the absorption transmission. This is basically nothing but transition, electronic transitions. Metal can absorb any photon, and by capturing energy in this way from the photon, electrons can go from the field part of the conduction band to higher empty levels, or from the basically for metal that is what happens in metals, conduction and valence bands are occupied with the metal electrons. So, once the electron absorbs the energy, it goes to the higher empty energy levels, and when it comes back a photon is re-emitted. This is the standard thing happens in most of the metallic materials. But in case of dielectrics or even some semiconductors, what will happen? If its valence band is full and there is nothing in the conduction band, there is energy gap, as you see here delta E gap is written here, this is what is energy gap. Now, therefore, if a material is a material cannot absorb any energy photon provides, it can only absorb the energy which is given by delta E gap, and when this much energy is available, energy will be absorbed by the electrons go to the high energy level and then again comes back to the low energy level by transition, and this will be followed by emission of a photon, right. So, in the case, both the cases what we are having is absorption and transmission taking place by the electronic transitions, whether it is metal or a dielectric, this happens in both the cases. Only thing difference is that the way it happens in case of metal is different from in case of dielectrics. Then other than that, you have some kind of what is called reflection or refraction, basically not reflections. You can also have bending of lights because of the present change of the media, and this is dictated by the Sen's law, okay. Well, and the last thing is what is known as a luminescence or photoluminescence. Luminescence is nothing but emission of radiation by solid at relatively low temperature is what is called as a luminescence. Photoluminescence is a light emission brought about by absorption of high energy photons, typically ultraviolet. The most widely utilized form of photoluminescence is the fluorescence. All of you know fluorescent microscopes, in which light emission is immediate, takes by the allowed transitions. But you can also have phosphorescence, in which slower conversion of the excited energy into light happens, and that means the emission of light is basically delayed, and this is basically due to formating transitions. So, you can have both photoluminescence as phosphorescence, depends on what type of transition is taking place. If the transition is fast and allowed, many transitions allowed, then it will be photoluminescence. Whether if it's forbidden and slow, then you can term as a photophosphorescence, okay. So, now but most important thing is that whenever you are whenever we are shining a light on the material, transitions, electron transition do happen, and in case of most of the semiconductors, valence band is full, conduction band is empty. So, therefore, if I have a photon falling on the valence band, electrons in the valence band will absorb the photon energy, and then if it can jump from photon to valence to conduction band, then it will do that, provided the photon has sufficient energy to cross this barrier of the what is called as the energy gap. Now, it can also happen that this transition will lead to obviously the electron movement from valence to the conduction band, and then electron can come back also and lead to photon. That is what we have discussed now. But what can also happen is that because of the transitions, sometimes the electron can come back and electron and hole can remain together, and this is what is known as exciton, okay. That is something which is not happen always, but do happen. But as I said, emission of light is also possible, when you transport an electron, or basically when you and an electron jumps from this valence band to the conduction band, and then it comes back because of energy reduction, photon can be emitted. And this is something which is we will be discussing a lot today. By the way, so excitons are basically very interesting thing, excitons, as you know. Okay, so what actually happens? Why do you think of exciton actually? Let me explain again. At low temperature in the bulk semiconductors often show optical absorption just below the energy gap, just below this band gap actually. And this cannot be actually the case if we think of this is the band structure. Okay, I have a photon energy coming into picture. If this photon has sufficient energy to drive the electron from the valence to the conduction band, then only the photon will be absorbed, right? Otherwise, why the electron will absorb photon if we cannot have a transition from valence to the conduction band? But in semiconductors, bulk semiconductors, what has been observed is that, very simply at low temperature, that this optical absorption can happen below the energy gap. So this is very not easy to understand why it will absorb a photon energy which are less than the energy gap, because that will not allow the electron to have a transition from valence to conduction band. So that's why this process can be associated with something known as a exciton. What is that? Formation of electron and a hole bound to each other. Electron is basically extracted, or basically electron has absorbed the energy, but it could not have a transition from the valence to the conduction band. So it stayed together with the hole which is there nearby, and they are bound to each other, and this thing is called as exciton. That means electron and hole bound to each other can be called as exciton. As for any particle, electrons, excitons are basically mobile, right? So binding energy between electrons and this hole is basically electrostatic, and that means the Coulombic attraction actually dictates the binding between this the electron and the hole, and that one can actually calculate it. Is basically nothing but minus e squared divided by 4. This binding energy is nothing but minus e squared divided by 4 epsilon 0 r square, right? That's what you know. And why it is that? Because Coulomb's law tells you that energy depends on 1 by r square, right? So this is something which is very important. Now, what is the effect of this binding? How does it is going to change the kinetics of the whole thing? Okay, that can because of the electrostatic interaction between this hole and the electrons, the energy required for the excitation formation leads to electrostatic reduction, interaction reduction. Okay, what does it mean? Compared to the unbound electron and the hole energy, the energy of this pair is much lower. Okay, so that means what? This electron which is at the valence band, energy compared to this energy of the electron, this pair has low energy. So if that is the case, if the pair has low energy, what will happen? That is nothing but electrostatic energy. This energy is reducing the energy gap actually. So that means what? They can then easily, if I shine a light, they can easily absorb, this pair can absorb the energy and move to the conduction band. That is what it is compared to a electron in the valence band. Well, and that means we can think of change of Bohr radius, and therefore we can always define a new Bohr radius, and this Bohr radius will depends upon mass of hole, mass of electrons, and also the zero mass of electrons, also as well as the radius of the Bohr radius. Okay, so that I have already discussed in the last lecture. Now, if you look at this Bohr radius or the Bohr exciton radius or exciton diameter is basically nanoscale. The value basically varies from 1.3 to about 28 nanometers. Silicon it is about 3.7 nanometers, okay, or 9 plus, or in case of gallium arsenide it is about 20 nanometers. Okay, so that means what? Because this has a nanometric dimensions, so it will be affected by the confinement effects of the size, as we have seen in earlier cases. So that means not only this density of states will undergo confinement because of the different class of nanomaterial, as well as also this exciton will also undergo transitions. That is what something we discussed in the last lecture, and we said that you see this is the values of the exciton diameters. So, they are nanometric. So, therefore, they will be affected by the size because of the confinement effects. To discuss further, there are different types of exciton. What we are discussing the Mott Wiener type of exciton, in which electron hole pair can remain together, and they can found in all non-metals like semiconductors or the dielectrics. For indirect band gap materials, excitons near the direct gap may actually exist. All excitons are ultimately unstable against recombinations. That is also true. They can recombine, and exciton complexes are possible. Like there can be 2 or 3 excitons can come together and complex also. It's not only that. So, what is the actual effect is this? Because the excitons are actually bound by electrostatic force. So, because of these, they can reduce this energy gap. As you can see, this is a conduction band, these are the exciton levels, or this is shown like this. So, compared to free electron which are there unbounded here, these energy levels are lower. So, that means it can allow faster transitions because of the absorption of the optical photon or optical energy. Am I clear? So, that is something which you should remember, and this we already discussed. Okay, this kind of spectra which is coming from the lead selenide, for different size of nanoparticles, the change of this optical spectra can be explained both in terms of nano size effect because of the confinements, that's for this kind of low low wavelength peaks, and the for high wavelength peak is basically because of the exciton. Well, so that is about the last lecture we have discussed. Now, let us discuss about something about optical emission spectra. Those are absorption. Well, optical emission I has already discussed about it. If we have valence and the conduction band, and if there is an optical photon falling on it, and this electron absorb this photon, well, this is for semiconductor actually, then it can move into the valence band or a conduction band because of this absorption of the photon energy, correct. And subsequently, this electron then fall back to the valence band, leading to release of the energy in terms of photon. But this is something which is very easy. So, this is basically one can tell that this is another kind of situations where exciton does not form, but electron hole recombine. A recombine of electron hole can lead to what is optical spectrum. So, if the electron hole they recombine, it can lead to optical spectra or optical emission only when energy released is within 1.8 to 3.1 electron volt. Then only the radiation which will be emitted will be in the optical design. Well, that is something which is very important, and this is what is known as a luminescence. Okay, luminescence. We have discussed already, right? Because of the quantum confined nanomaterials, the emissions of the visible light that can be tuned by varying the nanoscale dimension, that is 1D, 2D, 0D, it can be varied. Not only that, it can also be varied by changing the size of the nanoparticle or nanomaterial. Typical trend is the shift of emission peak towards shorter wavelengths, that is nothing but a blue shift as the size of nanoparticle decreases. This is what is normally found, but it can be tuned actually, that is a very important aspect of this. But not only that, another interesting phenomena which can be observed in many of the semiconductors, very interesting phenomena which people observe of late, is that what is known as the photoluminescence. Okay. Remember, this all we discuss. What is photoluminescence? Well, just let me discuss about these two plots which are taken from different sources, but available in the Michael Ashby's book. As you see here on the left side of the plot, what is shown is the emission spectra of cadmium selenide, zinc sulfide quantum dots of different sizes. Okay. Sizes means it can have 14 nanometers to about 25 nanometer sizes. What you see is long, big, intense peak of normalized photoluminescence as a function of lambda, and these are the peak value of the lambda. You can clearly see where the radiation has peaked. Okay. And so therefore, lambda max values are reported here, 520 to about 650 nanometers. Okay, so not only that, so more of the nanomaterial size, sort of the wavelength of visible light that is emitted. Correct. That is what is shown on the right side. You can see from blue to the red, depending on the particle size of cadmium selenide quantum dots, one can actually get photoluminescence in the whole spectrum. And this you must have seen it, many of you must have heard it from different books or different literatures. This is very common. Okay. So what does it tell? Due to quantum confinement, the shift from blue to red corresponds to increase of nanoparticle size. In this regard, an issue of importance is the use of homogeneous distribution nanoparticle, because fluctuation in size and composition can lead to inhomogeneous spreading of the optical spectrum. So, we need a very, very narrow distribution of nanoparticles to see these effects clearly. That is what is done by Professor Don Seo from the Arizona State University. He and his group has taken very narrow size distributed nanoparticles of cadmium selenide quantum dots, and then once they irradiate with some kind of a radiation, these nanoparticles show optical emissions. Okay. That is what is known as a photoluminescence, and it is very, very easy to understand why this thing happens. This is mainly because of this phenomenon. Okay. So, the moment you shine a light of a particular wavelength or particular energy which correspond to the energy gap between the conduction and the valence and the conduction band, this electron absorb this energy and goes to the conduction band, and then later on the electron can come back or fall back to the conduction valence band and combine the whole, and the process can generate a light. This whole thing will depends upon basically the size of the nanoparticle, okay, and also the dimension of the nanoparticle, okay, because of quantum confinement effects. Correct, because electrons can only be staying in a particular, I remember, go back to my discussion on quantum confinement, electron can only stay in definite energy levels because of the confinement effects. So, if you shine a light of that energy, it absorbs it and goes to the conduction bands, and when it falls back to the valence band, emission happens of the optical photon. Okay. So, that is something which is easy to understand. But what about metals? Metals are also equally interesting. Correct. This is taken from Professor Anand Subramanian's of IIT Kanpur. Metals also show colors. Gold nanoparticles were used as a pigment of ruby colored stained glass dating back to 17th century. I have already discussed it, right, in the very beginning of my course. So, 1 to 10 nanometer size particle gives rise to this kind of color, and this was exploited heavily by the artisans in those days. They are exploited very heavily. So, they show a very ruby colors, or actually they can show different colors, but the higher size or the 10 nanometers and more normally shows a ruby color stained glass. Not only that, thin film of gold, which is obviously less than 100 nanometer, can show blue violet light. So, the color of nanoparticles will depend on the size in the nanoscale regime. Bulk gold is golden, that is why we like it, right? Yellow color metal, most of the women in India wants to wear, wants to put on as a jewelry, but nanoparticle of gold will not be yellow. It can have different colors depending on size, like red, purple, blue. Color depends on the size as well as shape, and also dielectric properties of the medium in which you are kept. Why this happens? This mainly happens because of the surplus plasmons, and the surplus plasmon or plasmons is a new concept to you. What is a plasmon actually? Let us first talk about that. Plasmons are nothing but a quantized waves, okay. And you may be thinking, what is quantized wave? Wave, right? Waves, light is a wave actually. So, they are actually quantized wave. That means their wavelengths are quantized. They cannot have any wavelengths. They have only very few values of the wavelengths. Okay. That is why they are called quantized. It is very easy to talk in terms of energy, because energy is easily can be explained in terms of quantized facts, right, from the quantum mechanics. So, wavelengths can be converted to energy very easily. You know that energy is equal to h nu, that is hc by lambda. So, I can convert energy into wavelength into energy, right. So, that means this plasmons actually quantized waves, they have quantized energy, and you know, they propagate to the material very easily. And how they propagate? They propagate by the collection of electrons, which can be altered from the equilibrium positions. Okay. They basically move from one part of the material to other part of the material by this collection of electrons which are there. And these electrons you know, can be altered, the energy can be altered, or they can be altered from the equilibrium positions by these plasmons. So, plasmons are basically readily observed in noble metals like gold, silver, copper, even others, those who have d electron bands or d electrons bands which are filled, they can be things like gold, copper, silver, and also metals like magnesium and aluminum. Plasmons can exist within the bulk as well as surface, both it can exist. These are quantized waves, move because of the collection of the electrons in the material. So, in fact, photons can couple with these plasmons, but important thing is the surface plasmons, which actually leads to color of the nanoparticles. That is what we will discuss more. What is surface plasmon? Well, you know, surface plasmons have normally lower frequency than this plasmon which is there in the bulk of the material, and they can easily interact with the photons. Okay. In fact, when photons couple with the surface plasmons, and that can lead to what is known as polaritons. Okay. Polaritons. Okay. This is nothing but coupling of photons with the surface plasmons, and this can lead to alternate regions of the positive and negative charge on the surface of the material. The moment the optical or photon interacts with the surface plasmons, okay, because the surface plasmon is also a wave, quantized wave. So, if you have a peculiar value or particular value of photon, incident photon, they can interact with the surface plasmons, and that can lead to alternative surface charges, positive, negative, on the material, and this can lead to electric field, correct. In other words, this interaction between the surface plasmon and the optical light actually can be thought of a, you know, light waves being trapped on the surface. Okay. Light wave getting trapped on the surface of the material as a result of this interaction. Okay. And this can be further emitted, or I can actually give you more further descriptions of that. The surface plasmon resonance, all of you heard, can happen when, you know, confinement of small particle size can lead to enhancements of the radiative properties of the nanoparticles. Okay. And this can lead to multi-modalities for the many applications, like gold nanoparticles can be used for cancer research because of the, you know, the surface modification capability, which allows them to bind with certain kind of proteins you know, formed by this cancer cell, and then one can actually tag this gold nanoparticle with some drug. So, whenever these gold nanoparticle are coming with the cancer cell, this drug will be released and the cancer cells can be killed. So, this is very commonly been done in the medical sciences. Okay, another way, what is now to explain you further what is surface plasmon, let me just go to this picture. Okay, before that, let me tell you that I will come back to it, don't worry. So, that means what? Many of the metals like silver, gold, all of them show surface plasmon, and resonance or these kind of optical emission spectra. As you see here, these are shown at different temperatures for silver, 400, 500, 600, 700, 800. A stands for 400 and E stands for 800 degrees Celsius temperature, and the peak shifts to the you know, lower wavelengths as the temperature increases, correct. And well, this is something to do with not the temperature, but calcination temperature. So, this shift is basically because of size reduction. As the size gets reduced, there is a blue shift happens. Same thing has been seen in case of gold also. You can see in 1948, 22 and 9 nanometers, gold particles show strong optical emission spectra at wavelengths of different wavelengths 600, 500 or maybe even less. Okay. So, this is very common. The question is, why does it happen? Okay. Let us talk about that. So, when a metal particle is exposed to light, the oscillating electromagnetic field of the light can induce a collective coherent oscillation of the free electrons. Okay. As you know, metal particle will have free electrons, right. Metal has many free electrons. So, surface is basically covered with free electrons, cloud. Now, the moment light falls on these things, it has its electromagnetic radiation, oscillating electromagnetic radiation. Light has, as you know, that electric field and the magnetic field, they are alternating in case of light, which is a wave. Okay. So, these can actually induce a collective coherent oscillations of these free electrons. Okay. Remember, collecting and coherent. Collective means many electrons actually can oscillate because of the interaction of the light with these, and also it can lead to coherent. Why it will lead to coherent? Because energy will be not lost. That is why it is called coherent emissions of these oscillations of the free electrons. Correct. And electron oscillation around the particle surface can cause charge separation with respect to the ionic lattice. What does it mean? Basically, what it leads to is that because of these interactions, electron particle surface can cause a charge separation from the ionic lattice. That means from the basically core of the atom, that is the center of the atom, right. So, it can lead to then form a dipole. Okay, that is nothing but alternative electric field. That is what we discussed just now. And this dipole, forming a dipole which can oscillate along the direction of the electric field of the light. Okay, you understand that. So, first thing is that light falls on the metal, it can interact with the electrons, and the moment it interacts with electrons, it leads to formation of these charge separation, surface charges, positive, alternative positive and negative charges, because electrons are actually, light is inducing a collective coherent oscillation of the electrons. Okay, and this oscillation of electron leads to positive and negative charges. Okay, it is oscillating. So, therefore, the parts where electron is not there, it will be positive charge, part the electrons are there, there will be negative charge, and these alternative electron fields will be present on the material surface. Correct. So, that means what? It leads to a dipole formation, and this dipole can oscillate, basically oscillate between the along the direction of the electric field of the light, and amplitude of this oscillation will reach a maximum at a specific frequency called a surface plasmon resonance frequency. Okay. That means what? This amplitude of oscillations of this dipole will be interacting with the emitting light or the incident light, and it can reach a maximum value at a certain specific frequencies. Okay. And when it reaches that maximum value of specific frequency, what you see is nothing but a surface plasmon resonance. Correct. You must know about a resonance, right? And this sphere induces a strong absorption of the incident light, and that can be easily measured by these UV visible spectroscope graphs which you are seeing in these pictures. Correct. The sphere has a band intensity, and the wavelength depends on the factors like electron charge density, structure, composition of the material, size of the material, many other things, right. I am not going to discuss about Mie theory. Okay. All of you, so you know a little bit, this theory can explain many of this, but I am not discussing about that. I am just explaining how this kind of emission spectra can come up in the real sense. Now, one can actually control this emission spectra by shape of nanoparticles, structure of nanoparticles, or even by what is known as a variation in the structure also. There are a lot of many ways one can control that. So, the first thing you are seeing is the size of the nanoparticle altering these emissions wavelengths, okay, sphere wavelengths. Okay. So, from 600 to it can going down to about 500 nanometers. So, as the size decreases. Okay. So, that means there is a blue shift happen as the size decreases for the sphere spectrum. This is something which is very unique in metallic particles, and one can use this kind of concepts or this kind of measurement techniques to explain the presence of the to rather know the presence of the particular metal nanoparticles of different size ranges. This is a very frequently utilized tool. Okay. So, I hope you understand what is surplus plasmons and how it can be used for various kind of purposes. Well, so I am going to show you some more pictures. Let us talk about gold, okay, or different steps of gold. Okay. And in these different steps of the gold, as you see here, they can give us a tunable property by changing the aspect ratio, right. You can have gold, instead of nanoparticle you can have a gold nano rod, or you can see here this is like a rod here, okay. This is also rod, this is a rod, but the aspect ratios are different. Aspect ratio keeps on increases from left to the right side. So, gold nanorods of different aspect ratios will exhibit different dimensions, and different kinds of SPR, right. As you clearly see here, the aspect ratio of 2.4 to 5.7, size may not be varying too much, but aspect ratio can lead to different emission, correct. Why does it happen? So, again because of the surface plasmons interacting with the incident light, that can change because of these different aspect ratios, which is typically observed in here also. You can see this is all taken from a published literature, which is not very old, about 10 years old or so. One can also have issues like this. Beside this shape factor, optical tuning is also possible by variation, like you can create core cell structure, or you can create nano cage structure, right. As you can see here, left side is a core cell structure, the right side is basically the cage structure. Okay. These are the cage actually, you can see these are the gold nanoparticle within a cage, correct. On the other hand, this is actually core cell structure. Okay. And as you can see here, basically that by making it core shell or nano cage structure, one can change the optical emission spectrum very easily. So, not only the shape, but also different kind of structure and size can lead to different types of optical emission spectra. All are because of this surface plasmon resonance, or the interaction of these surface electrons to the alternating field of light, magnetic and the electrical field of light, which is very very clear and understandable, and can be explained in different ways. So, despite this interaction between the photon and surface plasmon, surface plasmon cannot be produced by the smooth metallic surfaces, okay, when it can come in contact with the air, mainly because when the moment of life is different from the moment of the surface plasmon. Therefore, to cause a change in the momentum, a thin layer of metal can be placed above these particles. Okay. So, that is, forget about that. Another way of introducing, so that is something which is shown here. Okay. This is something that happened like this, how the surface plasmon actually propagates, correct. That is something which already discussed about it. But another technique of inducing surface plasmon interaction is to roughen the surface, okay, by metal surface, and this can be done in two ways: by creating a parallel linear features on the surface of the material, or by randomly roughening the surface. Surface plasmon polytons can be used to cause extraordinary transmission, and this is the phenomenon whereby a metal thin films exhibiting a series of holes of surface specific size and periodicity can transmit more light at a certain energies than anticipated. That means, if you have basically holes, series of holes in metal thin films, okay. If you do that, these are the holes you see, okay. These are the different holes created here, or the metal nanoparticles and the thin films. If you do that, so they can actually then transmit more into light than the other part of the thin film. Okay. So, that is something which can be, this basically you are creating a surface feature on the thin film, and this leads to the change of roughness of the material, correct. So, this phenomenon is very widely used, and what is the reason behind that? The reason behind is basically resonance generated between the incident light and the surface plasmon polyton in the incident side of the thin film. As you can understand, by putting these metal nanoparticles, you can create alternative charges. So, incident light can actually interact with these alternative charges and leads to formation of surface plasmons. Okay. So, that means we can create different ways or different kinds of structures to induce circular plasma. Not only the size, but also shape, geometry, roughness of surfaces can be altered to have optical emission from the metallic. Okay. So, if I have to put these things together, we discuss about semiconductors optical emission, we discuss about metallic optical emission. In semiconductor metallic optical emission is predominantly dictated by the electronic transitions from the valence to the conduction band and the recombinations of these electron in the hole, right. And this can be tuned simply by tuning the size. And so, if you create different sizes of the semiconductor nanoparticles like cadmium selenide or lead selenide or zinc sulfide, then you can see the whole spectrum of the electromagnetic light spectrum, this whole visible spectrum by putting these different size particles into the solution, correct. And this can be used for various purposes, okay. Not only that, not only for the experimental things, but also technological aspects it can be used. And second thing I discussed about is the metal, okay. As you know, many of these metals like normal metals like gold, silver, copper, which has deep bands in the electronic structure field, they actually exhibit what is known as a separate plasmon resonance, okay. And plasmons are nothing but a quantized waves which can propagate to the material because of the collection of the mobile electrons, okay. They are basically generated because of the interaction of the light with the electron, leading to formation of the alternative charges on the surface of the nanoparticle. And once this charge is actually created on the surface of the nanoparticle, that is what we see, and these charges can lead to formation of dipoles, and the dipoles then oscillate in the electric field, the direction of electric field of the light, and this oscillation can lead to, this oscillation can be then can have resonance with the incident light at a certain wavelength and can lead to huge emission, and that is what is known as SPR or surface plasmon resonance. That is something which is very unique in metals, but this can be also alternatively created by making roughness in the surface of the metal, or this can be tuned by using different sizes of particle, different shapes of the particles, or different geometries like cage structure, all these coastal structure can be done. That is very routinely done in the nanomaterials. So, with this I will conclude my discussions on the optical properties of materials, okay. And so, we have finished about 27 lectures. As you said that I am going to wind up this course with 30 or 30 maximum 32 lectures or so, and this course is on both properties and the characterization of the nanomaterials. So, I must spend about 5 lectures on characterization of nanomaterials. Characterization can be different types, okay. If I get some time I will discuss about the carbon nanotubes and all these aspects, but that may not be possible if I take all the lectures, I wind up, or rather I have to take more time to discuss about the characterization techniques. With this I stop the lectures today. I will get back to you in the next lecture on the characterization of the nanomaterials. Thank you.